Hello everyone, this is Bradley. Today this is a fundamental tutorial talking about variations of instances in geometry nodes. We are going to use a golden standard method available in 4.3, and this is going to be a little bit different from a temporary solution I talked about last time in 4.2. Since this tutorial will be a little bit more official, I also want to talk about different aspects of related area. But on the other hand, I have to warn you at the beginning that this tutorial is not going to be about armatures, because geometry nodes do not support armature. So if you are looking for any kind of variations related with character, this tutorial will not really cover that aspect. But we may cover some similar aspect of it. It depends. But anyway, so let's start. So here we're in Blender 4.3, and I want to firstly talk about the concepts of field and attributes before we move on talking about how to solve it to make variations of instances. And this is a very classical example of cube and eevee sphere that I'm trying to use the set position node to define the vertices position of these two primitives. But I hope you to recognize that I only have one position node, which seems to output itself to the cube and the eevee sphere respectively. But in this case, the cube is still a cube, the eevee sphere is still a eevee sphere. This means this position node has to be the cube position and the eevee sphere position at the same time. How is that possible? This is actually because that this position node by itself never contains any data. So the linkage is not really outputting anything. It's rather a reference of the position data coming from this green geometry data block. That's why you can also see this solid line versus a dashed line. Okay. And you can basically see that as well if you are trying to take a look with the viewer in the spreadsheet. And in this case, if I'm viewing the cube set position, I'm not looking at this position node at all, but the green geometry data block contains the position node by itself to define this geometry. If you're looking at this eevee sphere, it's basically doing the same for the eevee sphere position. Okay. On the other hand, if you're trying to look at the position node without a geometry, then there's no data anywhere, because there's no data to pull. This causes some problems when you are trying to output this kind of field or attribute with this diamond shape socket to any kind of primitive, because there's no geometry coming before. So when you're doing that, it will just say this is an invalid link, and it's going to be a red dashed line along with this warning. Okay, and you do not see any cube anywhere, because this is just the equivalent to output a zero value vertices. Okay, and this is going to be the same for any kind of diamond shape, whether it's an index or an ID or whatever, anything else. What's very important is everyone is trying to use a random value node for this kind of cube, and you do realize it's a diamond shape because there's a diamond ID attribute being used. If you're trying to view that, it will just say that this is an integer field based on ID or index. Okay, so it's not going to work in this case. There's just no cube being generated. On the other hand, what you can solve that is you put an integer constant with a circular shape socket, and you plug that into ID. It will solve the problem. You do not see the cube because it says the vertices must be at least 1. Our random value is just too small. So let's plug that to integer 1, vertices maximum 15, and then we recover our cube with a random amount of X segments. And you can try to change this ID as a seed so that you can have variance vertices or segments created. Okay, this is a very important core concept about how we are going to solve instance variations later using this for each element. Okay, but before we move on, I also want to discuss a little bit about instances itself. Although this tutorial has been titled with instance variation, but it's actually not a very accurate description. Whenever we are talking about instance in Blender, not just the geometry node, it actually means that it's a shared data. For example, I have this plane, and if Alt D to duplicate that, and it's actually shared geometry data, so that you change one, you change another. This is to save the RAM usage, to improve the performance of computer, because you do not need to worry about vertices location of two different geometry. You just calculate one geometry data and you copy paste it to the other one. Then data is working. So basically the only thing that you can actually change is the location, rotation, and scale, along with a little bit other object data. But the main geometry data is always shared across, so that you change one, you change another. This also means that instance variation is actually not that possible in order to improve your performance. And here I want to remind you that whenever you are talking about instance variation, you want to actually think about the possibility not to really get the instance variation. Or for example, let's say fake it. And in this case, you can see these are actually identical trees, because these are the same instances. And by the way, you can download all these kind of group nodes from the link in the description for free. And in order to fake the variations of it, you can just get a random rotation, a random scale. So I have random rotation on the z-axis, and it looks a little bit more different because you're just viewing different angles of them. And you put a randomness to give a random scale. And once you get the amount of instances up, sometimes you do not really realize that they are actually the same geometry. Okay. This is just some minor ways of faking it. But if this is kind of a background image, do you think people will really care if they're 100% the same or not? I highly doubt. Okay, so I hope you to keep that in mind, because RAM usage or performance in geometry nodes is sometimes very important as we move on to talk about issues later. So here, let's make a real variations. Let's duplicate the node tree. And as mentioned earlier, we're not going to use these instance endpoints or instances because they must be identical. Instead, we're going to use for each element. It's basically a loop node for each element. So we are running a loop for each element of a geometry in a corresponding domain. So for elements in point domain, it's basically the point edge in the elements of edge domain is edge. So basically for each edge, for each point, for each face corner, spline, instance, and a layer, and so on and so forth. By default, it's just outputting the geometry. It's actually the same geometry coming from the most beginning. This is very unlikely what you want. I don't know why it's being designed like this, but anyway, what you actually want is the generated geometry. But in this case, it's still the identical result because we are actually outputting this element, which is every point. Okay. Let's make that more practical. Let's make a tree generators into the geometry. So you only see one tree, which is not actually true because there are only 34 splines in this tree, but there are 2000 splines in the final output because we only have one tree being collided in the same place. So let's separate them. We're going to use a transform node. So that's I only translate the geometry as a whole. And I'm going to take the position values And you do see that the diamond-shaped position has been transformed into single circular value because each point only contains a single position instead of multiple. And you plug that into the transform. You can see the trees has been distributed into each point, but they are still the same tree. Okay. And in this case, in order to create variations, we can take a seed into that. As I mentioned earlier, that we have all these kind of random values, and the reason it cannot be plugged into all these kind of transform nodes is because it's a field. But we can run through the same translation, the same transformation of a field to a constant, in this case, for an ID using an integer constant. This is basically the same concept. The only difference that I'm just going to use this index as a seed, so immediately you get the difference. And basically you can do the same with this index to the ID so that you can plug that into the scale. You can also plug the same for random rotation. So the index into the ID, rotation into rotation. Plug that into the z-axis. So you solve the issue. You need to solve a little bit of parameters, but anyway, I'm not sure if it's obvious, but they are 100% different, and you can change all these kind of parameters as you wish to make it more like a tree. Okay, and basically that's it. But you do realize that this is 31 milliseconds for 15 trees. But previously it's like I have 74 trees, but it only takes 2 milliseconds. You can increase the amounts, you can increase the changes, but it never increase the calculation of geometry nodes, because these are instances sharing the same performance or the same RAM usage compared to the actual real geometry being created on these locations. That's why I warned you at the beginning. If you're trying to make instances or a forest, it will be really heavy. Before I move on to talk about other important aspects of variations, I want to discuss a midway of two methods of creating variations or fake variations. That is, that we're not going to create as many variations as the amount of points we are generating. I'm only going to create a few, maybe 3 to 5 instead of 1 billion. So I can use a points node. So it's basically doing nothing other than just generating the amount of instances in the same location. So I do not even need this kind of transform geometry or anything, right? I do not need this position node as well. I can just delete that from this input field. So it's just the same tree at the same location. I mean different trees in the same locations. But I can transform that into the geometry to instance. In this case, geometry to instance by itself is not actually going to help the performance. Does it? Oh, it is. A little bit? Really? You're kidding me, right? Oh, it's doing something. I'm surprised. Anyway, okay, fine. I only create maybe 5 variations, and then I'm going to instance some points. Of these 5 variations on these locations, and I'm going to pick instance along with the method I discussed previously, that I'm going to plug the random rotations and random scales. So it becomes much faster. So it can be a forest if you want. Okay. So I think this is a good compromise, that you have some variations for each element, but also you save the performance. Okay, so this is a way of thinking. Finally, it depends on what you are looking for. Here, I also want to remind you that sometimes I do not really like putting a transform geometry inside and plug a position outside in order to transform whatever stuff. I don't think this is very intuitive, and somehow I just don't like it. Okay, so it's very possible that sometimes if I'm just creating all geometries, I may just plug the points into the for each element and then instance on point, and so on and so forth. It's very possible I'm going to do that. Another possibility is that if you're trying to plug this index into the ID in order to plug that into this transform geometry, I want you to realize that they are actually using the same seed. Because if their ID is the same, their seed is the same. Actually, they're basically the same random value being created in this case. It may not be obvious in this case, but it will be obvious in others. Okay, and in this case, you will probably want to change the seed values of this random node. Or another possibility is that you can take a index seed, so that from the single index you are creating different kind of seed that you can actually create, so that you can change one seed, that you can change the whole setup. I think this is more convenient, and this is more useful when you're creating a group node, just like what I'm doing with the tree generator here. Okay, it's basically the same concept. Okay, so let's move on to animation aspects of variations. So here, this is a very different examples. This is a stylized explosion effect I've made a tutorial about in the past. So you can take a rendered view, and this is animatable. If you turn on the balloon, it looks a little bit nicer, but it also becomes too shiny. I'm just going to go with the solid view in this case. And my goal is that I'm going to create 4 variations of it and explode it one by one. And to instance that, I'm going to just use curve linear, and I'm going to use instance on point, plug in these explosion units, plug in the count into 4, step side, so that I'm separating them. Very nice. But obviously these are instances, so they are sharing the same seed, the same geometry, and they are animated together. In order to create variations, we need for each element. And as mentioned earlier, that it's completely your personal preference whether you are doing the transform geometry inside the zone or doing the instance on points outside. Here, I'm just going to do everything outside. Just remember to take the geometry to instance, and you can pick the instance. And plug in this curve to linear into the for each element. And for some reason, it's not working. So now it's showing up. Okay, fine. And these are completely identical, unless you plug the index into index. You realize why it's the index, because it's coming from the index seed inside this explosion unit. Okay, these are discussed in the tutorials in the past, so I'm not going to repeat that. So that you can change the seed, so that you get a completely different setup of explosions, which is very nice. But they are still animated together. And in this case, you are just going to get different values of animations. And I have this delay for which is operating on the index. Essentially, it's just a kind of different subtraction of this index. For example, the index always coming from 0, 1, 2, 3, 4, 5, so that you have 0, 1, 2, 3. And 0 is not completing the animation, and 1 is always completing this explosion animation. That's why you have this effect. So if you have a different kind of subtraction, then you get a different type of delay, as you see from this delay 4. And in this case, I'm just going to use the preset, which is more convenient. So if I plug this index into index, just remember, if you do not plug this index, then it's a field, and it will not work. So now it's working, and let's change the step interval maybe to 35, maybe 25, and the duration to 35. So that you animate that exploding one by one, you get this animation done. Okay. In this example, as long as you can get different values for each element, it does not really matter how you do that. And we can do another example. Let's start with a grid. And I'm going to do a point distribute. Let's increase the scale of this grid so that they are more distributed. And here I'm going to use a proximity fold. I've made a tutorial talking about this proximity fold. It's essentially just a geometry proximity node. And in this case, whether you're whichever one you're using, you will have this red linkage, because this sampled position is a diamond-shaped socket, meaning it's a field. Okay. And to solve that, it can be very simple that you just plug that outside. And then you can plug that as a controller. And the concept is that closer to this empty, earlier it will explode. And you realize it does not work. The reason is that this instance index is following ID. And whenever you doing these distribute points on face, you're generating ID. So to solve that is actually very easy. You just plug an index inside. So you can see closer to this empty will explode earlier. So you can control how they explode. And basically that's it. Okay. And obviously another method is that you can just plug this for, but you need to output this position to the for each element so that you can transform that into a single value. Okay. There's no right or wrong about which method to choose. It's a complete personal preference things. But I believe you will choose the earlier one, because it just saves nodes and clicks. Okay. And yeah, basically that's it. There are so many different ways of doing the same stuff. And I don't think there's right or wrong answers most of the time. I'm also changing my habits over time to adapt different kinds of workflow. So anyway, I hope I've covered enough things, and I hope you enjoyed this video. I'll probably see you next time. Bye bye.